Okay, today in IM2 we're going to be talking about 3.7, which is comparing functions. So I did the work for this one because I mainly wanted you to be able to identify what kind of a function it is from the equation. So obviously this one is a linear, and we know that because there is no exponent on the variable. Okay, this next one, the variable that we're looking for is the exponent, which means this one is exponential. And the last one, the variable is 2, which means this is a quadratic. Okay, so what does that mean? Well, if we graphed these, and notice that this is comparing the motion of a car, distance per minute. Okay, so this is 1 minute, right? So in 1 minute, they're at the same place. And we can see that because they all equal 1. They started at 0 because they had not gone anywhere at 0. So we're going to compare them from 0 seconds on. Okay? So you can look at each of these graphs over here and see the difference. But I just want you to compare them, see what's happening. But they all intersect right here at 1 minute. So what do you think is going to happen after that? Okay, so then they ask you, this is the exploration on page 104, they ask you to fill out the table for the next 5 minutes, I think it is. Okay, so now they want you to do the next 5 minutes, and so you need to look at these graphs and tell me what you see. So take a second and do that. Okay, so the first thing is that this one has a constant rate of speed, and it's just going up, and it continues to go a certain amount of distance every time. Okay, this is the distance, and that's because this is the linear one, right? Okay, so what's happening with our exponential our exponential graph? So it's going up. Doesn't seem like it's going up by a lot, but then we start to notice that it's going up more and more and more. Each time it's expanding more and more. Okay, so we see that it's accelerating, so is this one. Okay, and this one is ahead until we get right here. And from then on, this one is ahead. And this one's going to go up faster and faster and faster. So as our graph looked before, where they all intersected, okay, like this. Okay, they all intersected here. The exponential one, the parabola, the quadratic one, is going to maybe come out like this. The exponential one's going to go out fast, and the linear is just going to keep going. So they just want you to notice what's happening with each kind of graph. And then the question number 4 was, which function has a growth rate that is eventually much greater than the growth rate of the others? And that would be the exponential graph, because at this point it starts growing more rapidly because this is getting larger each time. This exponent is the same every time, but the base changes, but this is the exponent is getting larger, and so that's why it eventually will way overtake the other two. Okay, so this is just a little bit of a review for what kind of equations we're talking about. You should be very familiar with the linear equation. This is just showing you this is the independent variable, this is the dependent variable, and it's plotted normal, y equals mx plus b. Okay, this is a distance equals rate times time problem, and this is just a regular graph. Okay, an exponential graph is one in which the variable occurs in the exponent. So sometimes it'll look like this, and then you would say it occurs in the exponent. But in this case, right here on this one, it is the exponent. And that explains why it gets larger and larger. If you remember correctly, if the base, which is this number here, is a fraction, then it's going to be a decreasing graph. Okay, so it'll be shaped like this one. If it is a whole number, then it will be shaped like this. It'll be an increasing graph. Okay, and this is just when it has a reflection over the x-axis. Okay, a quadratic equation is what we've just been dealing with in the chapter before. So this just has some interesting facts. This makes it quadratic, has the shape of a parabola, and this is interesting. The name quadratic comes from quad, meaning square, because the variable gets squared. Okay, so now we're going to learn about first differences. So first, make sure that all your x values are going up by the same difference. It could be by 1s, it could be by 2s, but it has to be the same every time, and you always want to check that because that could alter your results. Okay, now we're going to find the first differences. This is the first differences, and we do find the difference between each of the y's. So 4 to 6 is 2, 6 to 6 is 0, 6 to 4 is negative 2, 4 to 0 is negative 4, and 0 to negative 6 is negative 6. I'm going to go over here. How much is this one going up? It's going up by 60 here, then it's going up by 90 here, and it's going up by 135 here. It's going up by 202.5 here, and it's going up by 304 here. So we don't see a real pattern there. And then the last one, it's going up by 3, by 3, by 3, by 3, by 3. My first difference is the same in all of those. Okay, so now what they want you to do is find the second differences. We don't need to find the second differences down here because they're already the same. So now 2 to 0 is negative 2, 0 to negative 2 is negative 2, negative 2 to negative 4 is negative 2, and negative 4 to negative 6 is negative 2. So these are our second differences the same. Okay, and in this case our first differences were the same. And if we were to do these over here, we're going to find that they don't get any better. This is 30, then 45. So we still don't have a pattern here, and 101.5. So we're not sure about this one, but what we can say about these, and this is in your journal on page 106, that a linear function, the first differences are constant. So there's a linear function. In an exponential function, consecutive y values have no common ratio. Or have a common ratio, have a common ratio. So let's look at the ratio of this to this, and we find that we have a common ratio of 3 over 2. If you multiply 120 by 3 over 2, you get 180. If you multiply 607.5 times 3 over 2, you get 911.5. So this is our exponential graph. And then the quadratic, the second differences are the same. They're constant. So this is one way for you to be able to figure out what kind of a graph you're dealing with. And it's pretty easy. You just do the differences each time. Just be patient and be careful. When you're doing it, make sure you continue in the same direction. So this is going up, so it's plus 2, stagnant, then going down 2, so it's negative. So always move in the same direction. Don't go up one side and down the other, because you will get different values. Over here on the linear, you're going up 3, up 3, up 3, up 3, up 3. So be very, very careful. Okay, I thought this was a really good example of how to come up with a function based on the table. So they're pretending that you didn't know what kind of a table it was. So the first thing that you do is you check your x's. Yep, they're all going up by 1. Then they did their first differences, which were all different. Down 12, down 4, up 4, and up 12. And then they found their second differences, and we find, oh, it must be a quadratic because the second differences are constant. Okay, so now that we found that out, the next step that we're going to take is we're going to write our equation, but we don't know what it is. We can't very well start here because we don't have any information except our y-intercept. So maybe what we learned in an earlier unit, maybe finding, notice here, find it because they gave us the 2 zeros. We can go ahead and use those. So I'm going to go y equals, don't forget your a, and then we're going to put x minus 1 and x minus 3. Now we're going to choose that other point, and I'm going to use that y-intercept, and we're going to plug that in. So we're going to go 12 equals a. We're going to plug the 0 in. 0 minus 1 times 0 minus 3. We get 12 equals a times negative 1 times negative 3. So 12 equals 3a. So a equals 4. So now we've got an equation. Y equals 4 times x minus 1 times x minus 3. Then you would multiply these together. You would get x squared minus 3x minus 1x would be minus 4x plus 3. And then you're going to multiply that all by 4, and you're going to get the equation that they got down here. So these are the steps you would take to go from a table all the way till you get a function. And of course, if it was linear, we would just have the same thing in mind, only it would be like this. Okay, with an exponential, we know that we start with this equals 0 and find our base, and then that would give us the rest of our equation. All right, so this isn't taught at Folsom High School, so it won't be on the test, but I wanted you to understand that when you're comparing functions using average rate of change, you can't compare a linear graph to the others because only a linear graph has a constant rate of change. So what you have to do is pick two separate points, and then you match those points on your exponential or on your quadratic, and then you would just compare that one little shot of time, one little piece of time, to the piece of the linear graph. And that's all you can do. So you could say, between A and B, what is the difference between the two? Which one is accelerating faster, etc. And the same thing for over here. So this explanation of that concept is in your book. It's very logical, but I'm not going to take time to go over it now because there's a really good problem in the book. Okay, so this is examining the difference between two different kinds of fish. This is something that the Fish and Wildlife do. They introduce species into lakes. Usually they use the ones that have already been in that lake because they don't want to introduce something that will kill everything, and they want to introduce the ones that will survive the best. But they have these two different species and they're trying to compare them. So the first thing we look at is this one's going up. Let's check our first differences, right? And we find that the first difference here is 164, and it's the same for every one. So this species A has a linear graph, okay? And then species B obviously is either exponential or quadratic. It looks like it might be exponential, but it's hard to tell. But all we're going to do is start with, they want us to compare year 0 to year 4. So we're going to use this point and this point, and we're going to use 0 to 100, and we're going to use 4, 300. And now we have two sets of points for each, and we're going to compare them. So here they are compared. Here's species A, the linear graph, and it's growing at a rate of 82 fish per year. Yeah, 82 fish per year. Species B is growing at a rate of 50 fish per year. So we can see that species A is growing faster than species B. And do you think that's going to continue? Because this one starts at 100, same place, but it's going up, and at 10 years, let's look at 6 years. It's 592. So at 6 years, it's 592, which is right about there. So do you think it's going to continue to have the same rate? What do you think? Okay, so the next problem is asking you to compare year 4 to year 8. So now we're going to use these 2 points, and we're going to use that same 4, 300, but we're also going to use 8, which is this point, 8, 800. So now we're going to compare them again, and what do you think we're going to find? So you could do the work if you want right now, because I don't have the work to show you, I just have the answers. So if you want to push pause and do the work, go ahead and do that. But here are the answers. So species A, this figures, it's a linear graph. The rate of growth of the fish is going to stay the same. And then the rate of the other one has increased quite significantly. And so it's now growing much faster. And they will continue to get farther and farther apart. So depending on the goals for the fish, what do they want with the fish? Maybe they just want rainbow trout. So it doesn't matter to them that it's 82 fish per year because this is the desired fish. Or maybe they like this fish because it will profligate faster and they can give higher limits for the fish to the fishermen so that they can catch more fish. They have a limit per day or per week, and so then they'll be allowed to catch more if these fish are more likely to produce faster. So those are the kind of things you do in Fish and Wildlife. Yes, you can use math in Fish and Wildlife. So think about these examples as you do your homework tonight, and that's it for this video.